An empirical formula is the smallest whole number ratio of elements within a compound. Okay, and so what I'm talking about, the smallest whole number ratio, is that if I have a compound that looks like this, NH3, or a compound that looks like this, which of those is my empirical formula? The left or the right? Left. So why is it the one on the left? It's reduced. It's the reduced version of this one. Right? The ratio is still 3:1, but this is the reduced version. So this would be considered the empirical formula. This is something called the molecular formula, which we'll look at a little bit later. Okay, so the empirical formula is the reduced version, okay, of all of those compounds. Okay, so I'm going to kind of walk you through what the steps are to solve for an empirical formula, and then we're just going to try some, okay? Because it's not really a concept that has a lot of vocabulary with it or anything like that. It's just, you just got to practice, okay? So the way you solve for an empirical formula is, like, you have to start, your problem will be given to you, or you will need to start the problem with either a percent composition or a number of grams. That's usually how the problem will start. Okay, so if you look at the practice sheet I gave you, that's what the first one says. It says, what is the empirical formula of a compound that contains 89% gold and 10% oxygen? Okay, so that's how your problems will be worded. So you can either start with the percentage if you're given that, or if you're started with grams, like that's great too. Okay? Because once you have it in grams, you are going to convert each quantity to moles. So each individual quantity will be converted to moles. Okay? So that's really easy if we're given grams to start. If we're given percent to start, I have to make a little like step 1B here. Okay? If we're given percent to start, so let's say we're given 36% to start. What we do is we're just going to say we're using a 100-gram sample, which would mean we turn that into 36 grams. Okay, so if you're given percent to start, you're just going to switch that to grams, and you're going to assume I was given a 100-gram sample of this. Okay, so that's kind of step 1B. If you're given a percent to start, you just switch it right to grams. If you're given grams to start, then you're good to go. Okay, does that part make sense? So just like in 100%, right, our percentages that add up to 100, it's just acting like we're starting with 100 grams of our sample. So we switch that from percent to grams. Okay. Next step is once you've converted them each to moles, you will divide each, oops, I can't write today, each quantity by the smallest number of moles. Okay, and what that step does to us is it gives you a ratio of our elements. It gives us a ratio. Okay, so what this would look like is if element A has 0.5 moles present and element B has 0.25 moles present, what's the ratio between these two elements? Right? This one has twice as many, right? Twice as much of that element is present in this compound. So that step gives us a ratio. I'm sorry, what? Oh, okay. That step gives us a ratio. So what I would do is I would take 0.25, that gives us a 1, 0.25, that's where our 2 comes from. Okay, so it's telling us that element A is present 2 times and element B is only 1. Okay? Mm-hmm.
How do you write it if there's more than 2?
You would just do A, B, C, you know what I'm saying? You'd have all the elements listed and you'd pick the smallest mole and you would divide every element by that smallest mole. Okay? We'll go through all of this in example. I just want you to kind of see what it looks like here first. Okay? Last step is to build the compound. Okay, so now you can flip over to your example sheet, and we're going to start with that first example. All right, what's the empirical formula of a compound that contains 89.14% gold and 10.8% oxygen? So when it gives you these percentages, it's percentage mass, right? It's not just percentage of number of atoms. So what's our first step if we start in percent? We just switch it to grams. We turn it to grams. So that means I start with 89.14 grams of gold, and I start with 10.80 grams of oxygen. Okay, and I write them spaced out a little bit like that because I know I'm going to convert to moles. So I'm just giving myself some room to write my T-chart. Okay, now with each of those, we've got them in grams. Our next step is to convert grams to moles of each of these, right? The reason we convert grams to moles is that we can't compare elements gram to gram, right? 1 gram of hydrogen atoms is 1 whole mole, but 1 gram of oxygen atoms is a 1/16 of a mole, right? So they represent 2 very different quantities, even though it's the same mass. So we can't compare elements mass to mass, right? It's like, it just doesn't work, okay? So that's why we're converting them to moles. All right, so if I want to convert grams of gold to moles, I go grams of gold to moles of gold. What does moles get? The 1. This is an easy conversion. What always goes here with grams? And this is just a regular conversion from grams to moles. It goes molar mass, right? To go with grams goes molar mass. So we're going back to our conversion. The molar mass of gold you find right on the periodic table, right? Gold is a transition metal. It's found in the middle. It has the atomic number 79. So what's my molar mass of gold? Yeah, I can round that to 197. Okay. So now I find the mass. What's the mass of gold here? I'm sorry, what's the moles of gold? Right, I multiply across the whole top, divide by the whole bottom, just like a regular unit conversion. 145 Did you say 145 or 0.45? Okay. I will tell you that with empirical formulas, when we're doing these problems, it's important not to round moles too early. Right? I would think with moles here, I want you to go to 3 decimals usually. Okay, because if you round them too early, it can throw our ratios off a little bit, and we just want to be careful. So I want to keep this at, I had it at 0.453. Is that about what it should be or close? Okay. Just so you just don't have to run into problems. Don't round that to 1 decimal. Make sure you keep it out a little bit further. Okay, so that's moles of AU. Now if I want to convert from grams to moles of oxygen, I know moles gets the 1. And then to go with grams always is molar mass. So oxygen's molar mass is 16. Okay, so I've switched to grams. I've converted all to moles. Now my next step says what? Divide by the smallest number of moles. So when you do this, one of them should automatically be a 1, right? Which of these is our smallest?
143.
So when I divide by 0.453, that should automatically mean that there's a 1 somewhere, right? Because you have to divide something by itself. So I just say 1 AU, so 1 gold atom, 0.453. We divide both of them by the smallest amount. This one we come out with 1.5. Okay, so we're not, just stay right there for right now. The last step is to do what? Build our compound, right? Build our compound. So gold and oxygen put together is an ionic compound. So which needs to come first? Gold, right? Usually they're listed in the order they need to go. Like that's just a little side note here. So if you're unsure when you build your compound, just put them in the order they came in the problem. Okay? When in doubt. All right, so if I start building it, I would say AU 1O 1.5. Does that look like a legitimate chemical formula? No. So what's the problem with it?
It's too small.
Right? Can I have a 1.5 oxygen atoms? So how can I fix that?
Double it.
I can double it, right? If I double it, that gives me the same ratio, the same proportion, but now I have AU 2O3, right? If I double one of my atoms, I got to double all of them. Okay, so this still provides us the same ratio, 1.5 to 1, but this is the smallest reduced version, which is what an empirical formula is. You can't reduce 2 and 3 anymore, right? So that is the smallest reduced version of a formula. So AU2O3. Okay, so this one says it's a 140 gram sample. We don't really care about that, right? We don't care about the fact that it's 140 grams because they gave us all of our individuals already in grams. So we just start with that. We take out that first 1B step of switching the percentage to a gram, right? Well, they already gave it to us in gram, which means our first step will be to really convert to what? To moles, okay? So I say 2.24 grams of hydrogen, and I convert that to moles. So in all of your conversions, what does moles get? The 1. And in all of our conversion, we were going grams to moles. So grams goes on the bottom to cancel it out. Grams goes with molar mass. So the molar mass of hydrogen is 1. Molar mass of nitrogen is 14. Molar mass of oxygen is 16. So do we have any questions about where these numbers came from or how they got plugged in? Okay. Now go ahead and calculate your moles. So once we reach this step, what's our next step? Divide by the smallest number of moles. So which one is technically our smallest? 2.22. So I'm going to take each of them divided by 2.22. 2.22. Okay, with hydrogen, right, that's essentially going to give us what? 1, right? It's really, really, really close to 1. So then we build our compound. 1 hydrogen, 1 nitrogen, 3 oxygens. Okay, nothing came out as a crazy decimal when we found our ratio, so we didn't have to double it or triple it or do anything like that. Can anyone name that molecule for me? Say it. What is it? No. Nitric acid. NO3 is nitrate. We added the hydrogen on the front, which means it's nitric acid. Okay, questions on that one? Go ahead and try the middle one on your own. All right, so you tried this one on your own, and I'm seeing most people have what I think is the right answer, and it looks something like this: N2H8SO4. Okay, so the process is the same no matter how many elements went into that. Although this is the correct answer, and I'll accept the answer like this, can you think of another way it should be written? No, not H first, but that's a good idea. Yeah, Cesar?
NH4.
Yeah, NH4 2 SO4. Right, it gives you the same ratio, but now it's a correctly written ionic formula. So it's ammonium sulfate. Right? And you don't have to be able to do that. That's not, the first answer is totally acceptable. I'm just, making an extra point. So it is a real compound, ammonium sulfate. Okay, but yes, this answer is totally acceptable. Okay? Molecular formulas. They are non-reduced. Versions of empirical formulas, basically. Okay, so if you have these examples, oops, wrong way. Right, one of them is empirical formula. All of them are molecular formulas. Okay, they technically all are molecular formulas. But only one of them is the empirical. So 1, 2, or 3, which one's the empirical formula? 1, right? That's the empirical formula. It's the most reduced. So all of them are technically molecular formulas, but empirical is the most reduced. So all empirical formulas are molecular formulas, but not all molecular are empirical. Right? So that makes sense? Yeah, make sure I say that right. These are molecular formulas because they're non-reduced. So the way you solve for molecular formulas is really, really similar, okay? You will take or find the molar mass. Find the molar mass of the empirical formula. And then step 2 is divide the molar mass of the molecular formula, which will be given. Sorry, I'll write it out. By the empirical. Okay, then that will give you the ratio basically, and you'll be able to distribute that. And I'll just walk you through that. It's not very easy to write it down in terms of its rules. Okay, so take a look at the back page. Now, we're going to just try an example. I think molecular formula is just easier to see in an example form than to write out the rules for it. So let's look on the back on that first one. It tells us the empirical formula of a substance is CH2O. CH2O. And then we've got some unknown mass, unknown sample that has a molar mass of 180 grams per mole. So we know it's a version of CH2O, but we don't know which version it is. Right? Is it C2H4O2? Is it C3H6O6? Right? We don't know what version of it is. So the way we do that is we find the molar mass of our empirical formula. So let's do that first. Okay, carbon is 12 plus 2 for hydrogen plus 16 for oxygen. Right? Are we good with finding molar mass that way? Do I need to write it all the way out? We're good with that. 12 is carbon. We have 2 for each hydrogen atom. And then, 1 for each hydrogen atom, which makes 2. And then 16. So 12 plus 2 plus 16. 30 grams per mole. That's the molar mass of the empirical formula. So now we're going to look at what's the ratio between the molecular formula and the empirical formula. And we do that by taking molecular divided by empirical. Okay, so you do molecular formula divided by empirical formula. Okay, and these are the molar mass of each. Okay, molar mass of the molecular formula, molar mass of the empirical formula. That gives you a ratio of 6. So what that's saying is that this particular unknown molecular formula is 6 times heavier than the empirical formula. That's what it's saying. It's 6 times heavier than the empirical formula. So the way we put that into a new chemical formula is we say 6 times CH2O, which equals C6H12O6. Seems simple enough, right? It's molecular formula, molar mass, divided by empirical formula, molar mass, gives us this ratio, and we distribute that throughout our empirical formula. Okay, this molecule is 6 times heavier than its empirical formula. Okay. What happens if these two are the same?
That's the answer.
Yeah, that means the empirical formula is also the molecular formula. So we're looking at that particular example. Okay? We should never have a fraction, though. Right? Empirical formula should never go on top. Molecular formula should never go on bottom. You should never have a fraction. Right? So if you've got a molecular molar mass bigger than your empirical molar mass, we've got a problem. Okay? You always have a whole number ratio. You should always get a whole number ratio in this answer. You don't ever have to double it or anything like that.
So, what if, like, you get, like, 6 plus 5?
Yeah, it won't happen.
Oh, okay.
Okay? It won't happen. But that's a good question. It couldn't. It couldn't happen. One of the molar masses would be wrong if that was the case. Okay, so if you do get something like that, I would check this molar mass. Okay? Okay, how are we feeling? Pretty good? You want me to just give you your homework, or do you need to do one more practice? The homework is both of these things, so I think we're good with just practicing that. Okay. So homework is a mix of molecular and empirical.